From knowledge bases to ontologies. This is episode 6, Query, Validate, and Build. Last time we read the formal stack, RDF, RDFS, and OWL, and you learned to read an ontology line by line. But a stack of definitions, just sitting there, does nothing at all. So today we put it to work. There are 3 things you actually do with a live ontology. You query it, to pull answers out. You validate against it, to keep your data honest. And you build it, the very first place from which everything else flows. 3 verbs, and the tools that make each one real. So here is the whole episode, in 3 plain words. Query. Validate. Build. First, querying. Once your knowledge lives inside a graph, you need a way to ask it questions, and that is SPARQL, the query language of the semantic web. Second, validation. Real data is messy, so you need a way to check that it actually obeys your ontology's rules, and that is SHACL. And third, building, because before you can query or validate anything at all, the ontology first has to exist. We will look at 2 very different ways to build one, by hand, and with a language model. Query, validate, build, let us take them one at a time. Let us start with querying. If you have ever written SQL for a database, SPARQL will feel both familiar and a little strange. Familiar, because it has that very same shape, a select, naming what you want, and a where, describing the conditions. Strange, because it does not query tables of rows. It queries a graph of triples. SPARQL actually offers 4 kinds of query. Select pulls back a table of results, the one you will reach for most. Construct builds a brand new graph from what it finds. Ask answers a simple yes or no. And update changes the data itself. But the heart of all 4 is the same beautiful idea, you describe a pattern, and the engine finds every part of the graph that matches it. Let us look at a real query, because it is far simpler than you might fear. We want every graduate student supervised by Professor A. Watch closely how we say that. Select, $S, give me the thing I will call S, where, and here are the conditions. Professor A supervises S. And, S is of type graduate student. That is the entire query. Those 2 lines are triple patterns, triples with a blank left to fill in. That $S is a variable, a hole in the pattern. The engine then slides across the whole graph, trying every possible value for S, and hands you back exactly the ones where both lines hold true at once. You never told it how to search, you only described what a correct answer looks like. And that one idea scales up beautifully. The real power of SPARQL is graph pattern matching across many hops. Each line you add is simply one more triple pattern, one more edge that a valid answer must satisfy. Want the students supervised by Professor A, who are also enrolled in a course taught by Professor B? You just chain the patterns together, S is supervised by A, S enrolls in C, C is taught by B, and a shared variable, appearing in 2 lines at once, becomes the join that links them. The engine walks these connected edges through the graph, following relationships several steps deep. This is exactly the kind of multi-hop question that is painful in a table of rows, and entirely natural in a graph. So we can ask questions. But here is an uncomfortable truth, your data will not always behave. Someone adds a course with no teacher. Someone types a date into a field that was meant for a name. You need a guard at the gate, and that guard is SHACL, the shapes constraint language. Think of it as a souped-up version of a database check constraint, but far more expressive. With SHACL, you write shapes, formal descriptions of exactly what valid data must look like. Then you run your actual data against those shapes, and SHACL reports back, precisely, every single place where reality fails to match the rules. It is how an ontology defends its own integrity. Let us make that concrete, with the simplest useful shape there is. We want to enforce one rule: every course must have at least one teacher. In SHACL, we declare a node shape, and we aim it at the class course, which becomes our target. Then we add a property constraint on the path teaches, the minimum count is 1. Now we feed in our data. A course that has a teacher passes silently. But a course with no teacher fails, and SHACL tells you exactly which course, and exactly which rule it broke. Notice the clean division of labor here. OWL lets you infer brand new facts. SHACL checks the facts you already have. Reasoning and validation are two genuinely different jobs. All of this needs tools, and happily, the ecosystem is rich and mature. To author an ontology by hand, the classic choice is Protégé, a free visual editor out of Stanford, with a reasoner built right in. To store and serve large graphs, you reach for a triple store like GraphDB, or a graph database like Neo4j. To run SPARQL queries at scale, frameworks like Apache Jena, and its Fusiki server, expose a proper query endpoint over the web. And to drive every bit of it from code, Python hands you Owlready2 and readflib libraries that let you load, reason over, and query an ontology in just a few lines. Authoring, storage, querying, scripting, a complete, open tool chain, free to begin with today. Which brings us to building, and the first path is the careful, handcrafted one, in Protégé. It follows 5 clear steps, and they are genuinely worth memorizing, because they are the natural order of ontology design itself. Step 1, define your classes, the kinds of thing in your domain. Step 2, define your properties, how those things relate to one another. Step 3, add your axioms, the constraints and the rules, the disjointness, the cardinalities. Step 4, add some individuals, a few real instances, to test that the whole thing hangs together. And step 5, run the reasoner, let the machine classify everything, and check for contradictions. Classes, properties, axioms, individuals, reason. That loop, repeated and refined, is how a rigorous ontology is born. The second path is brand new, and it is moving very fast, letting a large language model do the heavy lifting. Instead of hand-typing every class, you feed the model raw text, documents, manuals, a domain expert scribbled notes. The model reads it and proposes an ontology structure, suggesting the classes and the relationships it can see. It can go further still, completing the picture, spotting concepts you forgot, proposing axioms you had never thought to state. And it can even assess quality, flagging the places where the ontology looks thin, or inconsistent. In minutes, you hold a first draft of something that used to take weeks. But do hold on to that one word, draft. It is a starting point, never yet a finished artifact. So which path actually wins? Neither, and that is the real answer. The manual path gives you precision and control, but it is slow, and expensive, and it does not scale to a truly huge domain. The language model path is fast and wonderfully broad, but its output is unverified. It will quite happily invent a plausible-looking class that simply does not belong. So the winning strategy, today, is fusion. Let the model draft, and let a human refine. The model proposes the structure in minutes, the expert then prunes, corrects, and certifies it. And this is exactly where formal verification earns its keep. You run the drafted ontology through a reasoner, and through SHACL, so that fast and correct stop being a trade-off, and quietly become a pipeline. Let us see that scripted path in real Python, because it is wonderfully compact. We import Owlready2. We get an ontology, simply by its web address. Then, inside a plain with block, we declare a class, course, and a property, teaches, in ordinary Python, just by subclassing. We add a couple of individuals. And then comes the line that does the magic, sync reasoner. In that one single call, a real description logic reasoner runs over everything, classifies it, and infers every fact that quietly follows. After that, you can list the instances, or fire off a SPARQL query, straight from your code. The entire stack we have built across 2 whole episodes, driven from just a handful of lines. Let us pull the whole thing together now, into a single end-to-end checklist, the path a real project genuinely walks. First, design the ontology, scope it, and name its core classes and properties. Second, formalize it in OWL, by hand in Protégé, or drafted by a model and then refined. Third, populate it, load in your real instance data, to form the knowledge graph. Fourth, validate it, run SHACL, to catch every violation before it can spread. Fifth, reason over it, let the engine infer, and check the whole thing for consistency. And sixth, query it, finally ask SPARQL the very questions you built the whole thing to answer. Design, formalize, populate, validate, reason, query. That, in full, is the life cycle. And there is your working ontology, not a diagram on a slide, but a living system that you can query, validate, and grow. SPARQL to ask, SHACL to check, Protégé and the language model to build, and Owlready2 to drive every piece of it from code. But we have kept saying one word, almost in passing, reason. The engine infers, the engine classifies, the engine checks consistency. So how, exactly, does it do that? Next time, we open up the reasoner itself. Episode 7, Reasoning, where the ontology stops being a record of what we already know, and starts deriving the things we never said. See you there.